Okay, so hello everyone. So welcome back to our Rogers Efficient AI seminar, and so this is for our first talk in the new semester. And today, so we are very glad we have the Dr. Chen Luo from the Caltech to give us this talk. Partition is all you need, and it's a very interesting topic. Talk about the efficient large language model inference and training. And so here's some kind of the brief introduction to the Dr. Law, and he is currently a postdoc researcher in the Caltech, focusing on the AIM optimization. And before that, he was a researcher at the Microsoft Research. And his research interests are in bridging hardware constraints with the principle of the learning in neural networks. And he focused on the developing hardware-efficient learning algorithms that are principled and scalable for large-scale training, such as training the large language models, which is kind of right now very, very important topic in both academia and the industry. So today we're very glad we have the Dr. Luo to give us this talk. So now, Chen, it's your turn.
Yeah, thanks for the invitation, Professor Bo. Yeah, and also good morning, everyone. Yeah, I'm Chen Luo, a postdoc from Caltech, and I'm really glad to be here today to talk about one of bi-dimensional but often overlooked perspective of efficient AI, that is partitioning. Yeah, you can see the title of my talk is Partition is All You Need. Yeah, it's a playful on the well-known phrase in AI research, but you will see partitioning truly underscore many breakthroughs in both system, software, hardware design. And you guys are feel free to interrupt me in any case if you have any question. Yeah. So let's start. So here is a quick roadmap of our journey today. So first of all, I will define partitioning and explain why it is so crucial in AI development. And we will look at some historical example starting from GPU and ArcFlash and move into how partitioning apply to large language model. I will introduce DeepSeek, which has explored the idea of partitioning GPU resource themselves. And then we will move into my partitioning work applied to large language model through App Infra, which is just submitted to ICM 2025, and MST, which is accepted by Europe's 2024. And if we still have time, we can talk about some of the project I was involved when I was a researcher in Microsoft. And then we can end this talk and talk about conclusion and perhaps some of the future work. So let's start with today's demo. So I will give you a definition of partition. Partition is the process of dividing a large dataset or large workload into smaller, more manageable parts called partitions. Yeah. Each partition contains a subset of dataset or workload that is stored or processed separately. Partition enable parallel training and reduce contention, like dividing the workload into smaller units, allow the application to process each unit independently. The result is better use of resource, enable parallel training, parallel process for faster process time, and also help distribute the data across multiple storage device and multiple process device, reducing the load on individual device and improving overall performance. And I do believe you guys know that is not a new concept. We can see it on database. We can see it at distributed system like MapReduce, and beyond we can see on cloud computing like microservice. So it's always a hidden force and make the large scale system practical. So yeah, I do believe you guys all know that GPU was initially an example of partition in hardware. Yeah, GPU is designed to handle parallel operator, effectively do some of the tasks from CPU. We know initially GPU was designed for graph rendering. Yes, like when you play game, when you watch video, CPU will offload some of the graph rendering tasks to CPU because CPU's effective parallel processing ability. But soon you will realize you could partition and parallelize many types of computation, including machine learning tasks like training machine learning work, inference machine learning work that will be more faster and more feasible on CPU alone. Here is an example, also a big milestone in machine learning. That is AlexNet. Yeah, you guys know AlexNet was proposed on 2012 and also shaped the AI world by achieving unprecedented accuracy in image lab. And one of the main innovation of AlexNet was that it first used two GPU to speed the network. That's why AlexNet has a grouping and two of the splitting model architecture. They deploy two GPU and split the model into two of the group. One group is allocate on one GPU1 and another group is allocate on GPU2 and they deploy inter-GPU connection for exchanging the data. That is obviously a form of partitioning ML workload in multiple GPU device, parallelizing and enable the training across different devices. Is a landmark example of how partitioning at hardware level can yield, can push the developer of machine learning device. So let's continue. So from history of machine learning, you can see that the developing from convolutional neural network to LLM, and a big sign of this developer is we are dealing with billions, even trillions of parameters when the age of machine learning developer into large language model. And in that case, we cannot train or serve this model on single machine or single GPU. We need distributed setup and using some of the distributed training strategy like state parallel, model parallel, tensor parallel, pipeline parallel, sequence parallel, or 3D parallel strategy. And partitioning is the key. Parallel is about partition one part of workload or part of machine learning into massive scale and keep performance. So yeah, so recording that case as model size increase over time, we will have parallel training system, parallel training strategy about training on multiple devices in parallel, partition workload, and make it available on multiple devices. We have a lot of existing solutions like Amiga server, like Microsoft DeepSpeed, which deploy a data parallel and model parallel, and Spectrum from NVIDIA deploy data parallel, model parallel, and it is the origin of what the model parallel happen if Spectrum proposed them. So that's one perspective of how partitioning idea was deployed on large language model. And then we will describe another perspective that is, we know nowadays a very famous model called DeepSeek. Yeah. And if you take a look at this technical report, they claim that they use a GPU resource partitioning within their technology. They take HA100 GPU as example, and out of 132 of SM, 20 are allocated exclusively for communication, and 112 SM are allocated for computation. That is basically you can consider they sacrifice about 10 to 20% of computational ability for communication. Why it is why it is effective? One of the reasons is that the GPU they use is HA100, and you guys know HA100 is a customized GPU that constrain interconnection capability but maintain overall good computational ability. So using that partition, I do believe all the following ways our understanding, our investigation based on our experiments on partition and system. But we do believe they use this part of SM, this part of processing ability to do the communication. And that is actually a common practice in distributed training. You can sacrifice some of the GPU processing resource to do the task like or reduce, task like compression, task like decompression, so that you can reduce the workload, reduce the threshold on the bandwidth, but still maintain a good performance. So that it come out using this technology to solve the problem of HA100 bad interconnection capability. So if you are still interested in how it works, we recommend some of the like related work that was developing on partition area or system area. That is one process at 2020 of ISCA and one process on NSDI 2023. They talk about how to overlapping the interconnection communication, especially or reduce performance, and how or machine, how you can sacrifice some of the GPU to driven network, driven DMA to improve the whole performance. Yeah, that's how I do believe that's how DeepSeek partitioning originated from. So yeah, I think you guys have some question, or if not, we are trying to move on my work here. Yeah. So okay, look like there's no big question. So yeah, that's how the historical of uh how the historical of partition is going. We provide 3 examples of AlexNet, of GPU, and an example of DeepSeek to show why the partition is important. Then let's move on to, yeah, we will provide one of the work. The first work we want to discuss today is head infra, which is trying to address a key bottleneck in large language model, how to influence a long context model on consumer GPU like RTX 2040. Yeah. And this is because the LLM multi-head attention can be computational expensive, especially as the model grows in scale. So we want to provide a technology that partition the attention head intelligently, overflow and prefetch them on demand. This work is cooperate with Professor Bo, Jia Wei, Professor Beidi, and Professor Alima. So let's start it. Yeah, here is the background. As we dive deeper into conventional AI, like code generation, reasoning, planning, and AI agent, long sequence processing has become increasingly crucial. Like some of the foundation models, such as Llama, QW, Gemma, Missile, and all of like DeepSeek has shown significant achievement, but face challenge with memory management, but particularly during the training and inference extremely long sequence. And that's our primary motivation to optimize our memory usage without any performance reduction or sacrifice any accuracy in quantization or specification. So here, let's take an example like running Llama 3AB with 1 million token. Yeah, that is a challenging task because they require 207 gigabyte. Why it requires so much memory, even memory larger than all the GPU existing on the world? It is because first, it will require 50 gigabyte of weight. 50 gigabyte is 2 times of AB when you are using 14.16 format for computation. Yeah. And that is the minor part. We have 64 gigabyte of activation and also the most big part, 128 gigabyte of KV cache, larger than the sum of all remain. So you can see that there's a result that with a consumer GPU like RTX 4090 with only 24 gigabytes memory, we will hit out of memory error when you are trying to deploy such model with long context input on consumer GPU. We do believe that's really block the user, really block the AI development that only big company with a lot of GPU, big company like OpenAI, Anthropic, Meta, Google, Microsoft can use the large language model. That's really not democratic in AI. So we are trying to solve this problem, and we explore that there are a lot of different existing solutions like chunk prefill, partitioning the input preparing sequence, and it can successfully reduce the activation but remain KV cache large. And we have KV quant that quantize the KV to AB, save 2 times of KV cache. And 4B KV quant quantize the KV into 4B, save 4 times of KV cache. And layer-wise offload the KV cache only fetch 1 layer of KV cache on demand, and it can save a lot of memory from 128 to 8 bit. But the problem remains if you deploy all of these technology, they are either saving a part of activation or a part of KV cache, but not solving others. And even we combine the best technology like combine the chunk prefill with layer-wise overload, you cannot serve RTX 4090 because the remaining KV cache is larger than the memory remain when you divide the 24 gigabytes with the weight and leave something for some other purpose like initialization activation. So there's coming a problem that those existing methods, those technology are insufficient for handling its training long context inference. This illustrates the need for efficient memory management strategy in LLM inference. So we propose our solution, head inference. a simple but effective solution based on headwise offloading. Headwise offloading is a technology utilizing the independence of multi-head computation. The key idea is that instead of storing uh, entire KV cache on GPU without offloading, or instead offload and prefetch a layer of KV cache on demand, we only keep a head of one attention head on GPU at any time. The rest of the KV cache is stored in CPU RAM, reducing the memory pressure on GPU. So in that case, we provide a solution by partitioning at finite granularity. We can maximize the memory efficiency with mathematical equivalence and throughput equivalence. We'll talk about why we can do that. So yes, yes, that's good. How we do that? Let's look at different level, different granularity of partitioning using an existing approach. We have chunk prefill that partition the sequence-wise input sequence into smaller threads so that it can save the activation, but remains the head and layer is two-dimension uncontrolled. Layer-wise overall, on other hand, split a layer, but remaining sequence and head two-dimension uncontrolled. With our head infra, it's developed based on all this partitioning across all the three level sequence, layers, and heads, optimizing the memory utilization. So we have three granularity. So in using the three granularity in detail, we will, during the implementation, we will have a three for loop corresponding to previous three granularity of sequence, layers, and head. That's how our implementation for inference within the prefill phase and decoder phase. We also deploy some of the optimizing implementation like async data transfer on 10 to 11, 25 to 26 with asynchronized data transfer using ping pong buffer. We deploy chunk prefill as it is internal nested with our word, and we deploy KV cache management by pre-allocate all the GPU memory for GPU resource and all the CPU memory for CPU offloading. Yeah. So combine all of them, we can achieve median level of inference in Llama 3 AB, and we can achieve best of the performance that we can inference 4 million of token in RTX 4090. But there's remaining a problem, whether this offloading technology, whether this headwise partitioning sacrifice or affect the overall performance. Yeah. So we do analysis using loop-like modeling. Loop-like modeling is typically an analysis technology for systems like this homogeneous system with GPU and CPU and requiring data movement and computation between GPU and CPU. Yeah. So the peak performance can be determined by two main factors. The peak computational capability here is the 165 for RTX 4090 and also I did see some record. Oh, now it's gone. Yeah, sorry. Let's continue. So, and also the bandwidth capability. Here for 4090, we provide high bandwidth memory of 1000 gigabytes per second, or PCIe from 25 gigabytes per second. And whether an operator can be determined as efficiency, it is mainly determined by, okay, sorry. I will, uh, yeah, I want to print something for you. Print something for you. Is this able to like printing? Oh, yeah, printing. Yeah. So one of the operator can be determined as compute bound operator if it is allocated in the right size, which can achieve the peak performance of computation, or consider as memory bound operator on the left side if the performance is bounded by memory movement and its peak performance is determined by its arithmetic intelligence. Its require computation from device by requiring memory movement. So we do this analysis and we found that for prefill stage, if you prefill a longer context, it can ensure high computational efficiency on the computer bound. All the operator will locate on computer bound area because as the context length increase, the computational requirement is a quarters, but memory movement is still linear. So it will keep moving right. So in that case, if you have longer enough context length, the prefill stage will keep remaining the computational bound. And we found that if you have 10,000 of context, whether you are using offload or not, you can provide same performance, same throughput, even with our head infra. But if the context length is small, if you only prefill 1,000 of context, then your peak performance will go down, going into memory bound, so and not sacrifice. Fortunately, we are dealing with long context inference, so that is not a big deal, and the REFAI model guarantee that our performance will be the same as non-offloading, and head infra partitioning the activation head. But activation head is naturally independent. So this partition will not change the flow divide by byte because the computational is partition so as the memory. Yeah. And also for the decoding part, decoding is usually on the memory bound part, memory bound side. So like using offloading or using our head infra will definitely slower than the standard decoding, and it is unavoidable task. But if we do compare our head infra with standard decode, and we also guarantee that we can provide the same performance as standard inference without offloading, and same performance as standard offloading. Yeah. So that's it. Yeah. Before that, we have one slide at the end talking about all the experiment result. Yeah, but our work, our archive submission is on proceeding, so that we cannot provide too much detail. But I have already told you guys everything most important. If you are interested, you can go to our GitHub to try our open source code, and we can provide best of the performance of 4 million Qualcomm inference on RTX 4090 with mathematical equivalence, as we didn't do any quantization specification or sacrifice any accuracy. And based on our analysis, we can also provide same performance during inference. Yeah, that should be it. So if you have any question, we are welcome to ask here. So yes, we do see that Ashley, I don't know you pronounce your name correctly. You're asking, is it the deprecation of GPU bulk? I do believe, let's see, you are asking like whether the GPU utilization can reach the peak, right? Whether partitioning attention head will sacrifice the GPU utilization, make parallel inefficient. Yeah. So my answer here is that if you are using long context inference, context longer than 10,000, the GPU's parallel can go into sacrification. This is because using such long context, the parallel on the sequence level will make sure that you have already used all the SM or all the tensor core within GPU to do your inference. So yeah, they have analysis. We do have an analysis, yeah, but we found that the quick bottleneck is still on the roof line or communication part, not the GPU utilization. So that's our conclusion. 10,000 of prefill can sacrifice, can make the GPU parallel more efficient enough to use all the SM without any of the block low utilization. Yeah. So yeah, that's a very good question. Do you guys has any other question? Okay. If not, we can move into the next paragraph. Next work. It should be here. No. Okay. That's it. Okay. So let's continue to talk about MST, mini sequence transformer. One of my work was accepted by Europe's 2024. Yeah. And yeah, as you have heard, one of our previous work was doing long context inference by partitioning in the headwise level to enable efficient long context inference on consumer GPU. This work is doing also follow the line of partitioning, but doing a task on training side. Yeah, training side that involving splitting the MLP and LRHAM during training to reduce the peak intermediate memory, peak activation for enabling long sequence, long context training. And this work is cooperate with Jiawei, Beidi, and Prof. Alima. And so, okay, let's start it. Yeah, as we said, our background is same, so we reuse a long context figure. You guys have shown in the first talk, first session or second session of head info. Let's just skip it, go directly into the true background of evolution of foundational model. Yeah. So here we help you provide a context of understanding the evolution of foundational model and how our work, how the MST align with the current trend. We observe a trend from Llama 2 to Llama 3 that they increase their vocabulary size from 32 to 128 of 4 time increase. And it also increase the MLP intermediate so as sequence length. They claim that such parameter change can guarantee better performance because you can use large vocabulary for embedding, large MLP for understanding, a large sequence for long context processing. And this trend is not only shown during the development of Llama, it is also shown in the development of like Microsoft Phi series and Google's Gemini series. We will talk about it in the end. But coming with this model change, those improvements also lead to higher memory consumption, which restrict the training of long sequence, mainly because of the MLP and LM hat, they generate a large intermediate value, large intermediate activation, bottleneck the long sequence training. This is how our solution, the MIDI sequence transformer, step in aiming to enable efficient training was 10 times to 24 times longer sequence, also providing mathematical equivalence and throughput equivalence during training. I do believe that's one of the main benefits of doing partitioning in AI. Your work are not like quantization and specification. All your work are mathematical equivalence so that you don't need to consider our work will affect ML itself, but you can focus on system improvement. So yeah, sorry, interrupt. Let's continue. So yeah, that's how the key finding and understanding coming from. In a traditional transformer architecture, there is a large intermediate memory required for MLP and L1 pad, and it is substantial as we illustrate in this figure. Yeah, you can see the right circle, and we can observe some memory spike here and make the peak memory usage up to 67 gigabytes. And you can also observe some of the small spike here. Let me try if I can use the pen. Yeah, here, some of the small spike here that is coming with the MLP. Yeah. So this memory bottleneck limit the sequence length because all of the peak memory is bottleneck, and it is bottlenecked by this large intermediate value here. So straightforward, we want to remove this intermediate memory. How? Yeah, we follow a similar idea like flash attention to, yeah, we can somehow call it flash MLP or flash LMS. It is we partition, splitting the input into mini sequence, mini subset, and we do the processing using the mini subset to generate an intermediate. The intermediate still large is not, but it is not large enough at whole state, and we can use the intermediate value to generate the output. Once we have output, we can intermediately discard this intermediate part so that we don't need to store, we don't need to maintain this such larger intermediate value on the GPU memory. Instead, we can do the computational processing on the fly. Processing, generation, discard, processing, generation, discard, discard, generation, until we have all the output and we just contact the output. It is like very similar to online softmax or online flash attention, like partitioning, processing, discard the intermediate, recover the output, but we deploy it on LM head and LM head. All of the reason is that because the attention has been already well optimized by flash attention or flash in some of these well-known attention memory optimization technology. The memory bottleneck of training are moving from attention to MLP and LM head. Yeah, so that's why our flash MLP or mini-sequence transformer can help to reduce the overall memory. Like you can see from the right figure, the memory peak is reduced from 67 to 47. You can see there's 20 gap save, but for memory, it is almost 10 times of saving. Yeah, so that we can use this technology by removing the intermediate, by saving, chunking, partitioning the computational of MLP and L head to mini sequence parts so that we can support longer sequence with throughput and mathematical equivalence. Yeah, that's the whole idea of this mini sequence transformer, mini sequence memory saving. Let's continue. So yes, follow all of these idea. We follow all of this previous idea. We have two of the key idea, or we call it key implementation. That is, we have input partitioning by splitting the input into multiple sequence. We have the sample of M, like defining how many mini sequence, how many chunks, how many sub partition here. So we have M sub partition. We do use the M do the computation sequentially and generate intermediate discard to generate the result. We split the input and use the gradient accumulation or output contact to restore the full output and gradient. So that's how our implementation goes. Simple but effective to optimize intermediate value, create more space for long sequence training, long sequence activation. So yeah, we continue to do analysis of memory efficiencies of MST. So originally, you can see that the intermediate memory is I. I is corresponding to the vocabulary size, and you guys know that's 128 of vocabulary size, will be larger than the hidden size of 4,000. So about 30 times larger. So that the I here is larger than the one layer's activation of A. So the total memory here, MST can use a partitional technology using a factor of M, leading like reducing intermediate memory into a subchunk. Like we reduce I into I divided by M, lower the intermediate memory. By using this lowering, we can reduce the total memory. Previously was W plus LA plus I, so times S. The total memory now would be W plus S times I divided by M. And such I divided by M is where our mini sequence saving. And we also have SQRT times A. This is another technology called activation recomputation or gradient checkpoint. This gradient checkpoint, is one of the technology OpenAI use. OpenAI use it for long sequence training and reduce the peak memory usage of activation from storing all of error layer, instead storing only SQRT error layer. So the we can draw a conclusion, the maximum sequence support of such using our MST together with gradient checkpointing is S equal to the memory of whole GPU minus by the weight divided by mini sequence intermediate as well as subpart of activation. The M represents how many mini sequence we have,
A represent activation memory usage corresponding to hidden size of 4,000. I corresponding to intermediate memory corresponding to the vocabulary size of 128,000, and weight, layer, and sequence. So this, for all of these computation, we can further reduce by using some quantization technology. But using quantization, we can divide this part by 2 or 4 if you're using 4-bit or 0-bit quantization. Also, you can use some of the offloading technology to completely remove the SQRT error into 1. If you are using the offloading, I do believe that some of the existing framework like Anslor's AI, they are directly deploy offloading together with random checkpoint, and our technology can directly apply on them to save more memory. Yeah. So that's how our analysis goes. We analyze the whole memory efficiency of MSD. So yeah, here we will provide results because all of this work has already been accepted. You can easily get the information from either our archive version or either our Neurops version. So yeah, this is how our mini sequence transformer goes. We can improve about 12 times to 24 times of sequence length and provide people of equivalence. Yeah, you know that Llama or Meta, they later published their Llama 3.1. They are using 60 GPU to achieve a sequence length of 128. But if they are using our technology, you only need 2 of the GPU to achieve 128 of sequence. Yeah, I believe Meta should deploy our technology, but that's other case. So let's just continue. We have the model we deploy all of this model like Llama 3, Llama 2, Qwing, and Gemma 2, and provide a context length extension from 12 to 24. The reason why the extension is different is mainly because they have different vocabulary size. Llama 3, as I said in the beginning, it has 128 of vocabulary size, and we can extend the context length by 12. Gemma 2, instead, they have 256 context length, 2 times larger than Llama 3. So as its memory extension, we can, using our technology, we can extend 24 times of memory context length, saving 24 times of activation memory compared to Llama 3. So right figure is a comparison for using MSD, using activation recomputation, and compare with standard technology of PyTorch. So that, as you can see, we all achieve 12 times memory context length extension or memory saving. But compared with activation recomputation, we can achieve 4 times. 4 times here for Llama 3, but only 1.6 times on Llama 2. The key reason is also the difference between the vocabulary size. The Llama 3, as we said in the beginning, has 128 of vocabulary size, and Llama 2 instead only have 32 of vocabulary size. So the activation recomputation can save a lot of memory for Llama 2, but it cannot reduce the intermediate memory. And if you recall our calculation equation in the previous stage, the intermediate memory will dominate the whole sequence, whole memory usage, so that we can provide a better context extension for Llama 3 instead of for Llama 2. And we provide equal tip ropes, equal throughput, and also some of the speed up of 1.1. This is because by saving sequence length, enable longer sequence, we can also use that technology to enable longer batch size. And longer batch size sometimes can enable more efficient training, especially when your context length is smaller. Increasing batch size from 1 to 2 or 4 can significantly improve all the throughput, all the key flops, all the throughput behavior. So yeah, if you guys are interested on Newport, we could recommend you to go and see our archive version or Europe's version of mini sequence. And yeah, welcome to. If you have question here, welcome to ask me here. Yeah, I think we're talking about 2 of these paper are almost run out of time. We may not have more time for any other work. So what do you think, Gamble? We can stop here and we leave the following time for question and discussion.
Yeah, I think we can reserve some time for the Q&A.
Sure.
Yeah. And so, yeah. So first, thanks Chen again for this very wonderful talk. And so for the audience, so you can either unmute yourself to ask questions or input your questions in the chat box.
Yeah, so so William Chin, your question is asking a paper. Yeah, we are on the process of archive. We do believe the archive version will be finished within week. Yeah, I think within this month we can see the archive version because ICML 2025 is just finish its submission about 1 week before, I do believe 1 week or 2 weeks before. And after ICML submission, we immediately start our process of archive. Archive sometimes take time to review your work. It is, I don't know how many times they require to review, but I promise you, we will give you, I think I will put the link of head info of its archive version on its GitHub as soon as possible. The archive there approve our submission. Yeah. So yeah, that's what I can ask. I will make it as soon as possible, but it mainly depends on archive part. And the paper will be ready sooner, immediately after archive approve our submission. Yeah, thanks, William.
So, any other questions from the audience? I think there's another question in the chat box, Chen.
Yeah. Okay, so Megha, you are asking whether we're using the simulation tool providing by SOC vendor. Yeah, a very good question. Yeah, I don't think we didn't use that, but we use the analysis technology, analysis tool provided by NVIDIA themselves. We use the on-site timeline analysis to analyze and the REFAI model. I do believe you are interested in how we analyze GPU behavior, how we analyze the REFAI model. NVIDIA itself, their on-site tool provide a way like to providing the kernel, providing all the estimate, the memory, profiling the performance, and they can directly pointing what part of the kernel, what part of kernel you are in. in the memory bound part or on the computer bound part. So yeah, the answer is that we didn't use any of simulation tool, but we do use some of the profiling tool to check whether a kernel is computer bound or memory bound using NVIDIA built-in tool of Nsight. Yeah, that's my answer. Yeah, if you have profiling tool, our idea is that if you don't have the access to GPU, the simulation tool could be useful. But if you do have the access to GPU and you can collect all the information from GPU, the profiling tool will be more accurate than simulation tool. That's our thinking here. Yeah.
Some other
So,
questions from the
yeah, I don't know whether you answer your question, but yeah, I think that's my thinking. Yeah, thanks so much. Yeah, thanks so much for your question. So yeah, so Hannah asking for ECE student with no background to get into this type of research and field. Yeah, what skill set can into handy? I think the best way to get into this research field is like find a mentor on this field who is expert here. Myself in Caltech, like I will give you an example. They have a class for CM 165, and the class is all the students. They will have a chance to select a project, and then within the project there will be a mentor mentoring you how you do the projects. Yeah, so if you can find a good mentor, either with a class, either with a class project, or in otherwise, you can directly email someone who you know who are using expert in this area, and ask the mentor to guide you, give you suggest, tell you what tool you do, what project you should use, and what code base you should try, so that it will be the most easier, most effective way for as a first step to get into this type of research or field. I do believe for can do some provide some suggest, but yeah, I do believe a good mentor is the best way to step in. But if you want to know some of the like whether you can do it on yourself to get familiar with area, I do trust that you can start with Hugging Face. They have a lot of effective tool. Like for example, we talk here about off-roading, talk here about activation recomputation, gradient checkpoint. And if you search this keyword on Hugging Face, they all have maybe exceeding tool, exceeding code base, so that you can test with that. And definitely you only have a GPU, but you can use like Google Colab or some of the cloud GPU to run your code. I think that's my answer. Find a mentor and try Hugging Face or have one GPU. Yeah.
Yeah, in addition to Dr. Law's suggestions, I think so the Ragas EC you can also to take some kind of the related courses in our department. So we have the machine learning concentrations in our in the in the graduate program. So there's several relevant courses ranging from the classical machine learning, the deep learning, and the distributed deep learning, and so on, and also the corresponding optimization courses. Yeah. So talk with the faculty in the department, and also and search around over the internet. Yeah. Yep. So other questions from the audience? So if no more question from audience, maybe I can leverage this opportunity to ask some questions. Yeah. So first, Chen, so because we collaborate with the first your first work, so I will not ask question about that. But I'm very interesting for your MST. So for this type of work, so can you go back to the slide that so showed the memory consumption breakdown?
Sure. Memory
Yeah,
broke down.
No. Next,
What is
next.
this one?
Yeah, this one, yeah. So here we can see that. So here you address the kind of the spike in the
Yeah.
yeah in this issue. So that's very good. So I have two questions. So first, so whether your method can also be kind of the combined with the other like the GLOW that to reduce the memory of the optimizer state. So whether it's kind of the orthogonal to others, yeah. So this is my first question. So in that case, we can further reduce the overall memory consumption.
Yeah. So a very good question. I think that's definitely able to combine with GROW to further reduce because you can see that we are reducing the activation. And if we use GROW, we can reduce the optimizer, and you can see that optimize occupy about I do believe it's 30 of the memory here of the optimizer. If we deploy GROW, we can further utilize optimize save the optimized memory. The reason we didn't directly apply GROW in our paper is because we want to keep it as mathematical equivalent so that we don't need to test some of the
Okay.
like whether the loss whether the model is changed during training. Yeah, so that may be easy and more easy for us, easy
Yeah.
for reviewer to understand how this work is done. So back to your question is that we can definitely apply GROW, but we consider it as a future work, not within this paper. Yeah.
Yeah, I see your point. And another relevant question that so here because there's also some other existing activation memory reduction method. For example, so very simple one that we can just use the recompute the checkpoint.
Yeah,
Right.
we already deploy checkpoint within our code without
Oh, okay, you already. Oh, so we already contain that.
memory.
Okay.
Yeah, we already do that. The checkpointing is another key point why we can save all this memory. And I do believe we have the total memory. If we not using the checkpoint, so I do believe the work is memory saving is about saving the key bottleneck. So in the early stage, key bottleneck is attention, and it is solved by flash attention. And after that, one of the key bottleneck is activation. If you are not using checkpoint, the activation is the key bottleneck, which here is previously is L times A, LA. And such a LA will be still the memory bottleneck because it occupies most memory. But if we divide using a checkpoint, we can change LA into SQRT LA. And as we see in the early stage, the intermediate memory, now become larger than, so I is less than LA, but larger than SQRT LA. So that makes the intermediate new bottleneck. So that makes our work handling the new bottleneck efficient. So I do believe memory optimization should always try to solve the key bottleneck. And this paper is because at the publication of this paper stage, I become the new bottleneck. So we solve it. So I do believe we definitely need to combine all of these existing solution. Like we combine flash attention, we combine random checkpointing. So yeah, so that make all other part now bottleneck. So we solve a new bottleneck. Maybe there will be new technology combined with that to achieve better performance. Yeah.
Okay. Thank you very much. And Another question, I think I promise this is my last question. So this kind of open questions actually. So what do you think what is the next? So because here, so we already optimize those the both for the inference and the training and for the optimizer memory, the activation and so on, and the KV cache in the memory consumption in the inference. So what is next, especially so we know that these days that so those are the
Yeah, I
the
think that
advanced those test time computers. So do you think that's kind of some kind of the new opportunities and challenges there? So maybe in the future we can also collaborate in that's some new direction.
yeah. So yeah, that's a very good question. I think so basically you need to see it from the developer of machine learning. So that in the development of machine learning, one of the trend we observe is they use longer and longer sequence, larger and larger models. Yeah, but that is how the scaling law is promising that you use larger model, you can provide better performance. You use larger sequence, you can provide better performance. That's how scaling law saving. And so that we can follow the scaling law, we can reduce the memory usage of all these component. But you guys all know that scaling law are going to hit its limit. So as scaling law hit its limit, I think the most important part is actually how to make the scaling law continue to grow. So that there is a modeling problem. As you can see here, some of the like long sequence model are not always providing better results than smaller sequence model if you are trying to see some of the median level model, like 4 million llama 3 are not better than 1 million or even 100,000 llama 3. That's the problem. That's the key problem, I think. If the model developer sequence extension, sequence scaling are bottlenecked by modeling. Then our system worker, our system researcher is also broken by the scaling law. So my thinking here is that we should first make the scaling law keep scaling so that our system researcher has something new work to do. So we always helping them. We always help reducing, helping saving the memory, helping speed up the throughput for best model. But if the best model is not changing, there's nothing we can do for the new work. So I do, from my perspective, one of the key perspectives that whether we can make a scaling or keep scaling. If we can, there's still a lot of machine learning thing we can do. If not, I'm afraid that we will run out of idea of the large language model, large scaling. So that's my thinking. Keep scaling is the most important task for us.
Yeah. Just following your comments, so to keep the scaling continue. So because right now we know that, so we can also have kind of test phase scaling, right? So do you think that from the system perspective, so is there any kind of new opportunities there?
Okay, so if that's your question, I do believe that the new ideology should be related with new GPU. If you can see, like the Flash Attention 3 is developing based on H100 GPU. They utilize H100's ability. So it is possible that, Grace Hopper GPU, they are using a very good interconnection between CPU and GPU. If you can have access to Grace Hopper using their extremely fast communication, I do believe you can support extremely larger memory by utilizing CPU memory, like CPU RAM, disk are much larger than GPU memory. And if you can access Grasshopper, use their high connection ability, you can increase the memory, scale it to unbelievable scale. And I do believe that if the problem remains, if we keep doing this, the key idea remains in the new architecture of GPU and try to use it. And we can see like some of the offloading technology may come into pricing, may be more useful here.
Okay, thank you very much. And
Thank you for
any other
that's
any
all of my today's talk, and we're glad to share my research idea with all of you guys. Yeah, that's what I currently believe in efficient AI research. That partition is all you need. Thank you. Have a good day.
Okay, thank you, Chen. So also thank everyone to attend our today's talk. Okay, see you next week. Thank you, Chen. Have a wonderful day.
Bye.
Bye.